Let's start. I'm going to do as yesterday and try to go more or less increasing the level of perceived difficulty depending on how many teams got the problem yesterday. I didn't really write down the exact numbers, I more or less remember, so it's not going to be exactly precise the order, but more or less. So that we can warm up with the simplest problems first and then get to the more difficult problems. Okay, so first I'm going to explain counting lattice squares, the second problem in the copy. I'm going to start by explaining something myself about the problem, and then I'm going to ask you if you want to make some comment, tell some additional solution, because in this case, even though we have one less problem than yesterday, since some of them have some difficulty or something that is worth explaining, I have to explain much more, so I need to speed up a little bit. Also, since it's the last day, Rodolfo is going to come at the end to say some words, some closing words. So since we have a tighter schedule, I'm going to try to speed up things by explaining first and then asking instead of the other way around. Okay, so counting lattice squares. So this problem, we are given an m by m grid of points by m by n means that this has length m, so m plus 1 points, and this has length n, so n plus 1 points. And we are asked how many squares of odd area we can make by choosing 4 points in this grid as its vertices. Okay? So, as we can notice from the drawings, basically each square is choosing some slope. So, let's say I choose this and these points to be the endpoints of one side. Then all the rest of the square is fixed. Okay? And also, so the slope of the two parallel sides is of course the same, and the slope of the two others, since they are perpendicular, is the inverse and the opposite. Like this is like we saw yesterday with the 2-point verticity problem. So there's plenty of ways to solve this kind of counting problems. Usually one tries to group all the things I want to count by some sort of metric that allows me to count all of the things that have the same metric with a combinatorial, the combinatorial equation, and then sum up in some way all the possible metrics. Like we can count by the size of the area, we can count by the size of the bounding box, we can count several ways to count. So the one I chose, because it was the most natural to me, was trying to group by the slope of the sides. Actually, so the shape of the side. So it's actually its length and its slope. Okay? So basically, by the shape of this triangle right here. Okay? So it's important that a triangle like this generates the same square as a triangle like this. Right? So we have to decide to count only one thing. Okay? And for each type of triangle, we can count with a simple equation that I'm going to show how many squares with that kind of shape there can be built, and then we iterate, not really iterate in the program, but we sum up overall possible triangles. So each triangle is represented by two numbers, which I will call the x and the y, which is the distance in the x coordinate and the y coordinate between the first point and the last. Okay, so this will be like the x, and this will be like the y. Okay, and as I said, if we have this pair and this triangle, and also we are also counting degenerate triangles. In the case like dy is 0, we count the flat triangle, and if the x is 0, we count like the vertical triangle. Okay, those degenerate cases are not really triangles, but still represent some squares. So we are actually counting pairs of the x and the y. So it's important that the pair dx dy is equivalent to the pair minus dy dx. Because if dx dy represents this triangle, minus dy and dx represents this triangle. Okay? Notice that the dx and dy are not exactly the length, but directly length. So if the triangle points the other way, we have negative dx, and if it points up, we have negative dy. Okay? So we come from the vertex that have the square angle towards the other two points. Okay? So we know these two are equivalent, and then we have some mirroring, right? If we have this kind of thing, if we mirror it, we have a different square, but of course the number is the same. Because mirroring the grid, you will get the same grid. So the mirror will be just, so if we mirror horizontally, we'll be just taking the opposite value for x and leaving y as it is, and if we flip vertically, it's opposing the value of y and leaving the value for the x first as it is. But of course, since these are squares, flipping any of the two ways is equivalent. Okay? Like if you can notice here, if we flip just this, or if we reach just this, we get different things, different classes of equivalence of the same pairs. Okay, so we have also minus dx dy, and flipping this will lead to dx dy dx. Okay? And of course, minus dx minus dy is equivalent to dx dy because it's just flipping the whole thing to the other side. Okay, so we will be like minus dx minus dy is this triangle right here. And dy minus dx is this one right here. Right? And all of them, it uses the same square, so there's not really no point of counting them all. Okay? So we have all these pairs that more or less induce the same squares, or the same squares and the mirrors of those squares. So we can think of all of them as a single equivalence class, right? And just count twice how many enter in a grid. Okay? And as you can see, it's basically for a pair of values, the number, all the possibilities of selecting the sign of each of them. For a pair of positive or non-negative values, all the possibilities of selecting the sign and the order will be in the same equivalence class, if we include the mirroring. Okay? So basically we just want to iterate or sum over all possible pairs, or at least all the pairs that induce an odd area square, and then count how many fit in the grid, and then multiply by 2 because of the mirroring. Okay? In some cases, we don't have to multiply by 2. So in the cases of when the square is aligned with the axis, we don't have to multiply by 2 because the mirroring is the same square. Okay? Is this clear? Good. So now, let's count for a given pair. So first, we have to do two things. First, count for a given pair how many squares there are in an m by n grid, and also which of these pairs have an odd area square. Okay? So for the area, it's just, so the only condition, so the area of the square is the side squared, and the length of the side is square root of dx squared plus dy squared, because of Pythagoras theorem. Okay? So the area of the square is dx squared plus dy squared, and if we want this to be odd, that means we want one of these to be even and one of these to be odd, right? And they are, and the square is odd if and only if the original number is odd, and then the square is even if and only if the original number is even. Okay, so basically we want dx plus dy to be odd. So we want one of them to be odd and one of them to be even. Okay? And as we said, choosing the order in which we consider the pair maintains the same equivalence class, so we can just fix, okay, let dx be the odd one, or let dy be the odd one. So basically we iterate over all pairs that have one odd and one even. And then we don't have to multiply by 2 because, and we have to multiply by 2 to consider the opposite. Okay? Because, so fixing which is even and which is odd, we can write them as So dx we write as 2x, and dy we write as 2y plus 1. Okay? Good. So now the other question is how many squares fit in the grid. So we can just see the size of this bounding box is clear that this is the x and this is the y, the length. The size of the bounding box is dx plus dy times dx plus dy. Okay? So since the bounding box is this, it really makes no difference which one is x and which one is y. Because the bounding box is also a square. So because since they are called x and y, we may think that we have to compare x with m and y with n or something like this. But it's not really the case. So it's fine to fix this x being the even one and y being the odd one or something like this. Okay? So now that we have with the bounding box, we have a square that is aligned with the axis, so it's easy to count how many there fit in the grid. Okay? So in particular, we have m minus dx plus dy plus 1 places where we can start. Okay? Think that like if this is exactly equal to m, we have exactly one possibility, right? If it's a little bit less, we have more possibilities. Okay, and then the same for the other side, n minus dx plus dy. Okay, so this is the number for fixed dx and dy. This is the number. Okay, now we have to sum over all possible pairs, right? So basically. So we have to sum over So now we're going to consider, so we're going to make dx be 2x and dy be 2i plus 1. Okay? So x can take any value up to the minimum of m and n over 2. Okay? Because we need dx plus dy to be less than m and less than n. Otherwise, the bounding box doesn't fit in the grid. Okay, so it's less than the minimum of both. Okay, so if for the sum to be less, of course dx has to be less, and for dx to be less than this amount, x has to be less than half of it. Okay? Yes? Okay, and then y. We sum from 0 to more or less the same, mean between m and n. Here we have minus dy, which is dx, sorry, minus dx, which is 2x, minus 1 over 2. Okay, because again we want 2y plus 1 to be less than the minimum of m and n minus dx. Dx is 2x. And then we just get this plus 1 less this minus 1, and the times 2 get this over 2. Okay, so these are the two summations that we need to calculate. And then for each of them we have to calculate this, which in terms of x and y is m minus 2x minus 2y minus 1 plus 1. Okay? Because this is 2y plus 1. So this we can cancel out. And then n minus 2x minus 2, because also we get the minus 1 and the plus 1 that cancel each other. Okay? Great. So now we have even better, because now that we fix that one is odd and one is even, only one of them can be 0. So we don't have really a repeated case in which only one of them, in which both of them can be 0. Since only one can be 0, we are only counting once the square that is the mirror of itself. Okay, so that's also a good property of this kind of division. So now this is the result. Of course, we cannot calculate the summation by iteration because these numbers can be big. But the good thing is that, so this is a polynomial and y. Okay? So as you may or may not know, but if you don't know, I'm going to tell you now. The summation from I, so you probably know this, right? The summation of 1 from 0 to, from let's say 1 to n is n. The summation of I is n times n minus 1 over 2. The summation of I squared is, I don't remember, I think it's n times 2n times n minus 1 over 6. It was something like this, I don't remember. And from I cubed is the sum of I squared, which is basically n times n minus 1 over 2 squared. Okay? So some of these so this and this you probably know, and this you may know or may not know. But it doesn't matter. I mean, what is important is that it always happens that the summation of the summation from I equal to 1 of 1 until n of a polynomial of degree k gives a polynomial of degree k plus 1 evaluated on n.
Isn't it n plus 1 then?
This one?
Oh, the summation of.
Oh yes, this one?
Yeah.
Yeah, I think this is the other one. This one. I'm remembering this by heart, so maybe there's some plus or minus 1. I'm going to send you a link with all of these if you want the precise numbers. So you may know some of this, right? Some are like the first two are really well known. So the important thing is that there's a theorem that says that this always happens, right? So theorem for every k. There exists a polynomial of degree k such that for example, for every k, so for every k and for every p, a polynomial of degree k, there exists q, a polynomial of degree k plus 1, such that for every n, the summation of I equal 1 up to n of p of I is equal to q of n. Okay, so we have a polynomial of exactly, and these degrees are exact. So degree k means exactly k. So if p is of degree exactly k, q is going to be a degree of exactly k plus 1. And moreover, the most significant coefficient is going to be 1 over k. 1 over k plus 1. Sorry. But that's not really important. What's important is that this is true. Okay? So I'm going to do the extreme quick proof because it's not really important for the course. And so what? I mean, there are several proofs. And you can also find a stronger. I'm going to send you a stronger version of this theorem that even tells you what are the coefficients of q based on the coefficients of p. But it doesn't matter. So to prove this, it's just you can consider this I. So let's consider I to the k plus 1 and n plus 1. Yeah. Yeah, k plus 1 minus I to the k plus 1. Sorry, I plus 1 to the k plus 1. So if we consider this subtraction, we can we know what this is by Newton binomial theorem, okay? But the important part is that this is I to the k plus 1 plus some polynomial of degree k, okay? Some polynomial in I. So basically this subtraction is a polynomial. This is p of I with p of degree k. Okay? So then the summation of I equal 1 to n of some polynomial. Well, let's start putting n to this. So this is p1, p2, so p3 of I of degree k plus 1. This summation is equal to the summation of this difference. Okay? Sorry, so we can, yeah, sorry, so this summation we want to prove that it's a polynomial of degree k plus 1. Okay? So we do induction on k. Okay, for k equal 1, since we have this, and for any constant, this is the constant times n, it's obvious that it works. For k equal 1, and then by induction, so if this has degree k plus 1, and this has degree k, okay? So the only thing that matters is what happens with the, so let's extract from the polynomial, we can extract everything that is not exactly I plus 1, so I to the k plus 1, okay? Because everything that is with the smaller exponent, we can do some other summations and we are going to obtain polynomials of degree less than k plus 2, okay? And then the sum of polynomials are polynomials of the maximum degree, so everything's fine. And also if you have some constant times I to the k plus 1, we can put the constant outside the summation. Okay, so really the only case that really matters is what happens with the summation of I to the k, or I to the k plus 1 in this case. Okay, and for that we subtract this and we obtain a degree of a polynomial of smaller degree, and then by the inductive hypothesis this is also a polynomial. Okay, of the summation of all of these, it's also a polynomial of small degree. So the only terms that remains is this I to the k plus 1 evaluated in n. Okay, because when we sum up from 1 to n this subtraction, all terms cancel each other but the first and the last. Okay, so the first one is I plus 1, so this one remains evaluated in n. Okay? So we get a single n to the k plus 1 plus some things that are just polynomials of small degree. But by small I mean smaller than k plus 1. Okay? Okay, this is like the extremely brief proof that there exists some polynomial. Okay, so we have the theorem right here. So basically, this summation here is a summation of y up to some constant that does not depend on y, of something that is a polynomial in y, if we consider n, x, and n constants. Okay? So all of this is equal to p of this, mean for some polynomial p, and this p of course depends on m, n, and x. Okay? Because the coefficients of this polynomial depend on n, x, and n. Okay? Evaluated on this. Minus 2x minus 1 over 2. Okay? But moreover, since the coefficients of this polynomial depend linearly on the coefficients of this polynomial, or I mean not linearly but just multiplying, you don't have to really exponentiate, then this is a polynomial on x. That depends on m and n, but it's a polynomial on x. Okay, so we can do the same thing with this summation and this polynomial. Okay, and obtain a polynomial that depends only on n and m, evaluated on this, and then we get a closed form equation that solves the problem, which is a polynomial of bounded degree. Okay? There are other ways to think about this combinatorial and more refine the way we think about the combinatories to get just the polynomials just directly, but this is the straightforward way to think if you know this theorem, so you are comfortable reducing summations. Okay? So then we have the polynomial. So we know there's a polynomial. We can so to reduce the polynomial, we have to know the coefficients. So we can know the full version of the theorem, or for the coefficients we can just say, okay, we know the degree of the polynomial, so we can just do a system of equations with the first k. So if the degree is k, we can just put the k plus 1 first values. We have k plus 1 unknown variables, right? We have the independent coefficient, the linear coefficient, the quadratic coefficient, and so forth. We have k plus 1 coefficients for a polynomial of degree k. So we can check the first k plus 1 values of the polynomial that we can evaluate just by adding the first k plus 1 values of the summation, and then we get k plus 1 points that the polynomial passes through. Okay? So we can either solve a system of equations with this with k plus 1 unknowns and k plus 1 equations, or we can interpolate these k plus 1 points and get the polynomial, whichever way you are more comfortable. Okay? So even if you don't know the full form, or the full form gives a strain equation with a lot of combinatorial things that may not be easy to calculate, but you can always calculate like this. As long as the degree is small, this is going to be fast. Okay? The polynomial, as you can see, is fixed for every test case, for every m and n. But oh no, you can get the closed form for every m and n, or you can get m and or you can think that the polynomial is fixed for some fixed m and n that come in the test case, but still you only need to work out a system of equations that depends on m and n. Okay, and it's of a fixed number of unknowns and fixed number of equations. Okay. So then this is the straightforward way. This is basically the first thing I thought about. Then I realized that it came to two summations, and I realized that the summations can be reduced by this theorem. So then it's just a matter of refining all the math. Okay. So that's a quick way also to figure out that the problem is solvable with this idea. Okay? Even if you don't do all this math precisely, you know that there's a solution, and then you can do it precisely and more or less estimate the difficulty of the problem and how long it will take. Okay, and then the super quick solution. So maybe by intuition, or because you know all of this is going to work out without even doing a single equation, you know that the solution is going to be some polynomial that depends on m and n, okay, of some small degree. Okay, so you can just assume that the solution is going to be a polynomial of small degree, and suppose small is, I don't know, 20 or 30, which is 30 is much more than the degree you're actually going to obtain. Okay, because each summation only ups the degree by 1. And then find the coefficient of that polynomial by checking the small values. Okay, so don't even put in paper the summation. Just say, okay, how much do I need to obtain for I equals 0, for I equal 1? For the first, we calculate by brute force, and then we assume it's a polynomial, and we get the coefficient for the polynomial, and then evaluate the polynomial in the values of the test case. Okay? But for that, you need to be really extra confident on the idea that math is going to work out. Okay. Well, I guess there's plenty of alternative solutions for it, right? Because I'm not going to go through all of them, because there's a lot of combinatorial ways to count this. Okay. It's getting late, so I'm going to speed up a little bit. Okay. Someone wants to make a question or comment or something? Okay. So the next problem is minimal subarray length. This problem is we are given an array of positive and negative values, and then we are given a lower bound, and we want the smaller, the shorter contiguous subarray that sums more than our given lower bound. Okay? So I'm going to comment two slow solutions and the group solution first. So first we can think of, so we have this array, right? We have the array, the input array A. Then first we build, since we need to know the sum of contiguous subsequences of this, we use the usual trick. We take S to be the array that represents the partial sums of A. Okay, so S of 0 is equal to A sub 0, S of 1 is equal to A sub 0 plus A sub 1, S of 2 is equal to A sub 0 plus A sub 1 plus A sub 2, and so on and so forth. And this we can calculate in linear time with a simple iteration. Okay? We probably did this several times. Okay, so now the problem is to find I and j such that S of j minus S of I, which is the sum of the interval from I plus 1 to j, okay, is greater or equal than x, and minimizing j minus I. Okay? Yes? Good. So we can fix one of these, right? Like iterate all possible j's or all possible i's. Okay? So if we fix, let's say, I, so let's go right. So we fix, let's fix j. This is easier to work out the equation. So we iterate all possible j's. So all possible right ends of this subarray. Okay? So if we fix j, then we obtain that we need I such that S of I is greater or equal, smaller or equal, less than or equal to x minus, S of j minus. Okay, we just put the x here and the s I. Okay? So basic, and we want also I to be less than j, or less than or equal to j, depending on exactly how we do the math. But say less than j. And we also want, of all the i's that have these two properties, we want the one that is closest to j, right? Because in order to meet, if we want to minimize j minus I, we want to maximize I for fixed j. Okay? So we want the maximum I such that this and this. Okay? And then we check which of these is better. So the question is how to get this. The maximum I such that blah blah blah. Okay? So we basically have some fixed part of this array. Here is j. These are the possible positions I that we can choose. And we want, you know, this already fulfills this condition. And then we want the ones that fulfill this condition. And from those, we want the one that is more to the right. Okay? So this is a known question for several data structures. Okay, I'm going to just explain one. So one way to do this is to, with the range mean, well, in this case it's range maximum query. No, minimum, because we want one that is one. So if we want to know whether there is a fishing line in some part, then it's just asking the minimum of all these values is less than this. If the minimum is less, then that means there's a possible I in this section. Okay? So if we binary search the size of this section, and for each we check a range minimum query to see if there's a possible I in that section to fulfill this condition, we can basically answer this question in time log square. Log square of j, which is the size of the whole thing, or log square of n, which is the size of the original array. Okay? And this in general is an n times log square n solution. Okay? I'm not sure about the online judge, but apparently for what I found online, this was too slow for the actual compost. So the good thing, with binary search, that's an even simpler solution. We can at the beginning binary search length of the output. Okay, because if we want the first one that works, and then oh no, we cannot. Sorry. No. Okay. So then we need to speed up this. So we can either speed up the first part, or we can speed up this log square query. Okay. So I'm going to explain that how you can do that with a segment tree, with a regular segment tree, actually with the same segment tree you use for range minimum query. So we have a tree. Okay. And then we have the array. Okay, such that each node of the tree, since the segment tree represents some segment of the array. Okay, so first we start with some initial segment, so initial contiguous part of the subarray. Right, so we have j here, and we want to find something here that is smaller or equal, less than or equal to some fixed value. Okay, so first we try this. If that works, okay, we found it. Okay, if it doesn't work, we want to start moving that way. But instead of just moving, we are going to first try moving faster and then refine the result. Okay? So the way we move is, if we are currently on a right child, okay, we move to our parent. If you are currently on a left child, we move to our left neighbor. Okay? So move to the parent means, move to the parent in the case we are in the right child means expanding the range we are searching by 2 times the current size. Okay? So if we are searching for, I don't know, this subarray represented by this node, and we move to a parent being a right child, now we have something that represents this. Okay? If we move to our left neighbor, that means moving, we are staying on the same level, so we are staying on the same size of range, but we move to the contiguous range right next to it. Okay? And if you implement the tree in an array, for instance, in a single array or one array per layer, which are the 2 simplest way of putting a tree in arrays, then moving to a left neighbor is just subtracting 1 to the index of the array, or adding 1 depending on how you put. Okay? I mean, all the nodes in the same layer of the tree are contiguous in the array. Okay, so moving to the left neighbor is something that you can do in constant time. Even if notice that the left neighbor may actually be the common ancestor with the neighbor can be really far away. Okay, so we really want to move fast without going to the common ancestor and going back again. Okay, but we can do that in some implementations of the tree. Okay, this is the case when you don't want to use the try version of the segment tree I explained the first time. Okay, so then basically we are moving that way. Okay? And when we move from here to here, it's okay to discard this range because we already know there's nothing there. Of course, for each range we check the minimum. If the minimum is less than or equal to, we know that, okay, in the current range there is something that fulfills this condition. So we found some range, and if it's not, we keep moving. So we stop this when, so 2 things can happen. Either you reach a node where you are the left neighbor but you have no left, so you are the left child and you have no left neighbor. Okay? If that happens, that means there is no I, right? Because you are covering some range that starts at the beginning, because you have no left neighbor. And, okay? So if in the current range still the range is not fulfilled, then it is impossible, and for the current chain there is no subarray to consider. Okay, which can happen. Or if we reach some node that represents some range that fulfills the condition, then we have to start going down to find the precise I. Okay, the way to go down is basically greedy. If the right child also fulfills the condition, then go right because we want the one more to the right. If the right child doesn't fulfill the condition, go left. Okay? So how many operations at this stage? First, notice that if we are in the left child, so if we move sideways, we cannot move sideways 2 times in a row. Because if we are in the left child and we move to the left, we arrive at the right child. So at least 1 every 2 operations is going to be going to a parent. So we have at most 2 times the height of the tree operation, so 2 log n moving up. And then of course we have log n moving down because it's the regular way of moving down in a tree. Okay, so the overall complexity of this operation is logarithmic. So we improve the time to do this query to log n, so we improve the overall complexity to n log n. Okay? Good. Any other idea? Okay. Good. Let's move on. So now, I don't know, waiting boxes was the next one? Probably. Okay, so let's do boxes. So in this problem, the story doesn't matter. We have some integers, and we want to know the number of subsets, or we also have a multi-set of integers, so with repetitions, so on and so forth. And we want to know the number of multi-subsets, so different multi-subsets that such that their sum is less than some fixed parameter. Okay? And also the difference between the parameter and the sum is less than or equal to anything that the complement, so let's say subset S. So we want the sum of S to be less than W, and we want W minus the sum of Fs to be less than any element, the minimum of the complement of S. Okay? Because we want that there's some maximality condition on the subset. Okay? And then for each subset we need to multiply by some combinatorics to know how many, so we consider all these subsets and we multiply by the number of arrangements inside the subset. Okay, the number of orderings we can put those elements. Okay, that's the statement, more or less. So the first you start with this with the regular dynamic programming approach. You say, okay, I'm going to consider all the numbers in order. I'm going to accumulate the numbers that are the same, because that will ease up the combinatorial part. Okay, so first we transform this into we have 1, 1, we have 2, 2s, we have 1, 4, we have 2, 5s, and we have 1, 6. With the dictionary of making or sorting and making pairs or something like this. Okay, this step takes a moment. Okay, and then we are going to, the regular way to proceed is to consider all possible numbers and then say, okay, how many of these I'm going to use? Right? Because that will make the calculations, the combinatorial calculations easy. Say, okay, first, will I use 0 or 1 ones? Then will I use 0, 1 or 2 2s? Then will I use 0 or 1 4s? Then will I use 0, 1 or 2 5s? And so on. And then use the dynamic programming to make that recursion run fast, right? So let's try this. So we need to, so what our recursive function is going to take? It's going to take an index that is basically represents which of these I mean. Okay? And then we need to know, okay, how much weight we have left. Right? How much more we can put in without exceeding W. Okay? So we're going to have W that's going to be decreasing, or we can make it increasing, it's the same, but okay? And then we have to know a little bit more. We have to know, for instance, so each time we select how many 2s or how many 5s we are going to use, we have to multiply, okay, the number of, so the number of ways is the recursion times how many ways there are to put those 2 5s inside the previously existing selected numbers. Okay, but the only thing that matters is how many are already selected and not which ones. Okay, so this is some contraction we can make. Instead of remembering the whole subset, we just need to remember the size of the subset we chose so far. Okay, so we remember, hey, the number of, so this is remaining weight. And this is chosen boxes. This is correct. Good. So the other problem is that when we reach the end, so when we want to know when we can stop, right? And we can stop. I mean, when there's no more room, okay? We want to know whether we can finish here or if we didn't fulfill the maximality condition, right? So if we do it this way, we have to add something that to know this. So one way would be to remember the minimum number of something that was left out, right? And then at the end make sure that the remaining, and only count when the remaining weight is less than that. Okay? So we can remember with an additional index, let's go J. So minimum box left. Okay? Great. This is a dynamic programming that works, but it's screwed up because we have n times n times w. And n I think is 100, and w is 1000. So this is like 1,000 million, and it's too big, right? And then it's more or less. Then inside the recursion is more or less constant time. While we have to iterate all the possible values for each given, so we have to iterate whether we choose 0, 1, or 2 choose. This is just the sum of the number of possibilities for each of them. So the overall number of iterations for that part is going to be exactly n. Okay? This is like the same like analyzing the DFS or the BFS when you iterate the adjacencies of each node, right? Overall, the summation of iterating all the adjacencies is going to be the number of edges. In here, the overall cost of iterating over the number of ones, the number of choose is going to be linear as well. Okay? So this is the cost of memorizing and calculating this recursive function is going to be the size of the table, basically, and this is going to be n cubed times w, which is too big. Okay? So then, also another way to do this with one less dimension, but it's also not going to work, is to brute force, which is the smallest box we are going to leave out. Okay? Once we fix that, then we know we have a fixed bound on what gap we can leave for the weight. But we have to calculate a different dynamic programming function for each of those cases. So we remove a dimension of size n, but then we have an iteration outside of size n, so we are basically of the same complexity. Okay? So a way to really remove dimension is to, instead of iterate which is the smallest box that I'm going to leave out, iterate how much weight I'm going to leave unused. Okay? So then we iterate those, there's W possibilities for those. Okay? And if we want to use, so we do leave, let's call it X unused. Then the result for this, then we don't care for shape, right? We know that we can only finish when you use the whole thing. Okay? But then we know, since we are going to leave X unused, we know that we are forced to use, to fulfill the maximality condition, the only thing we do is forced to use every box that is less than or equal to X. Okay? So basically we put in all the boxes that are less than or equal to X, and we start the dynamic programming right after. Okay, right after putting all those boxes. Okay, so we start with, so it's basically f of I, W minus X minus some number, some sum of the boxes that are smaller than X. Okay? And then the K of already chosen boxes. Okay, but we don't need the chain anymore. So the good thing is, so we have an outside iteration of W possibilities and this thing. But now this dynamic programming is the same for every possible value of X. I mean, you can reuse the same table, right? Because this table does not depend on the initial value of X. The initial value of X only changes what initial values, so which values of the function I consider. So it changes the I, changes the K, and it changes this. But the whole table is yes.
Change the base case. In the base case, you have to.
Yeah, the base case is just if I have weight 0 left, then I can count 1. Otherwise, 0. Right? Because I fix how much weight I'm not going to use. So for that to be true, we have to fill exactly the weight that we have here. If we reach 0, then okay, there's one possibility of finishing here. If we don't reach 0, then there's no extra possibility. Only keep advancing. Okay, so the base case here is if remaining weight equals 0, then the answer is return 1. If I greater or equal than n, so no more boxes, and this didn't happen, then return 0. Okay, these are the two base cases.
But when you choose not to put X, you have an interval of possibilities that can return the base case. Let's say you put the X you chose is 10 and the W is 1000, so you can finish between 990
No, I'm saying I'm going to leave exactly x and use, not up to x. Exactly x. Because and I try every x. There's, I mean, after I fill the box, there's some number of space unused, maybe 0. Okay, so I try how much that can be. It's going to be an integer number between 0 and w. Okay? So I say exactly x. So then, whatever weight I put here, I have to use it completely. Okay, so the base case is the same for every x. That's the important. That's the difference between the thing I said how to remove the shape here and here. Okay, that's the improvement. Okay. So then here we have a table which is n squared times w, which is big but enough to fit in time, and then the outside iteration really uses the same table, so it doesn't really add more cost to the overall complexity. Okay? Any questions? Any different solution? Okay, moving on. Oh, we are a little behind. So I guess the next one was 7-segment display, probably. So 7-segment display was not really a hard problem in the sense of you need a strange ID or anything. It's just log, and you have to be careful, right? So we are given basically some families of graphs that depend on the numbers. On how the numbers look in a 7-segment display, we are getting some families of graphs, right? We have the 0, which is a cycle. We have the 1, which is a small path. We have the 2, and then we are saying we have the k order. So we have this family. So this is the initial graphs, and then we have the k order, which is add k nodes in between these. Okay. Yes? Okay, so, and then we are given some input graph in a regular way input graph, and we are asked, okay, how is it the graph exactly one of these? So is it some digit in some order, and list all the possibilities? Okay? So the first thing to notice is that each digit can only be used once, right? Because the different orders, so different case for each digit change the total number of nodes, so the input graph can only be exactly equal to a digit in a single order. Okay? So that's good because we can just do some. And then we can calculate that order because it's easy to know the total number of nodes. Right? Because the total number of nodes is just, for a given graph of this, the total number of nodes of order k is n, the initial number of nodes, times m plus k. Right? We are adding k nodes per edge. Okay? So for each of these, n the number of nodes and m the number of edges is fixed. So the number of nodes in the graph of order k is this. So we check if it's possible if there exists a k just by subtracting and dividing. We check if for each digit we check is there a k that makes this equal to the number of nodes of the input. Okay? If there is, let's see if the shape is also the same. But at least the number of nodes has to be the same. Okay? Okay, so if we do that for every digit, and now we have to know how to check, given a digit and a k, whether the graph of that digit in order k is equal to the graph in the input, knowing that the number of nodes is the same. Okay? So one other good thing is that, so I'm going to give you, of course there's lots of ways of doing this with different lengths of code. I'm going to give you a way. So I think all these problems are approaching in the same way. You have to find some singularity that makes the further calculations easier, right? So if we find a singularity on these graphs, like a distinguished node or something, we can use that to calculate the rest, right? For instance, I don't know, in a path, if we know which node is going to be this one, then we can check whether all the rest behave the same, right? Once we fix a node, all the rest are singular. Right? If this is node A, then this is a node that is at distance 1 of A, this is a node that is at distance 2 of A, and we can name or define every other node. So, and then we can check in the input graph if there's exactly those same definitions. Okay? This is the best way to approach this kind of problem. And then paths are easy. are easy to check, so let's try to check paths. Okay? So, and 0 is kind of a special case, because it's the only one that is set. But, okay. So the first way I would do it would be to check the degrees. Okay? Because for every order, all the nodes that we add are of degree 2. Right? So then we know the multi-set of degrees of each one, right? So here we start with 6 nodes of degree 2. Here we start with 2 nodes of degree 1 and 1 of degree 2. Here we also start with 2 nodes of degree 1 and 4 of degree 2, and so on and so forth. We write down for every digit how many nodes. There are only degrees 1, 2, and 3. Okay, in the digits. And then, of course, for the k that we already calculated, we add k times m more nodes of degree 2. Okay? Then it's easy to calculate the degrees of all the nodes in the input, and then if the multisets of degree do not match, then the graphs are not equal. Okay, note that their multiset is represented by 3 integers, the numbers of nodes of degree 1, degree 2, and degree 3. If in the input we have something of degree more than 3, then it's not equal to any graph. Okay? So it's easy to represent these multisets. We don't really need anything complicated. Okay, so now let's assume if the total number of nodes is the same, and also even more if the multiset of degrees is the same, then we continue. So the good thing about this is that, in general, since all the nodes that are added with the order are of degree 2, if we have something that is not of degree 2, that's pretty distinguished. Right? For instance, in the 1 we have to have, in any order, we have 2 nodes of degree 1. If we also have that in the input, we know that those 2 nodes have to correspond to these 2 nodes. Okay? Same happening with 2 and with all the digits that are passed. With 5, which is equal to 2, with 7, and okay? Also 4 and 3 have 1 node of degree 3, so that node is distinguished, right? Now, at this point, we know that there's a single node of degree 3 also in the input, so that node has to correspond to this node. Okay? And then in the 8, the other case, we have 2 nodes of degree 3, so they have to correspond to each other. And since this is symmetric, we can correspond them in any way we want. So any correspondence has to work. Okay, so now we have some correspondences between nodes in the input and nodes in the digits. So for 0, we just have, if we know all nodes are of degree 2, we just have to check that the graph is connected. If the graph is connected, then it's going to be exactly the same. If the graph is connected and every node is degree 2, it is the same. And we already checked that the number of nodes is okay, so that's the check for 0, just that the graph is connected. And for all the others, now that we single out this node, we can check everything just by implementing a function that checks whether between 2 given nodes of the input there is exactly a path of a given length. Okay? So for 1, for instance, we take the 2 nodes of degree 1 is the input, and we say, is there a path of exactly the total number of nodes between these 2? If that's true, then great, we finish. If it's false, then it's not correct. Okay? We do the same for 2, for 7, for 5, all of them that are paths. Okay? But the original digit is the path, we do it all by using this function. For 4 and 3, we take this node. Okay, all my neighbors have to be one of these. So we can check which one is and then they have 2 kinds of, both 3 and 4 have 2 kinds of neighbors. 2 have the paths of a given length, and the other one has a path of a little bit more length. Okay, but we can calculate with math, which is the length. Okay, so we do a 4 with 3 possibilities of which is the different one, and then do this check of, is there between this node, starting at this node, a path of this given length? If it is true for all 3, then okay, if not, okay? And then for 8, it's a little bit more difficult because we need to find the matching between the neighbors, right? We need to match this neighbor with this neighbor and this neighbor with this neighbor. But since there are only 3 of them, we can try every possible match, and for each of them check if there exists paths of appropriate length between them. If there exists such path, then for some matching, then we found that the graph is equal to this, otherwise it's not. Okay? So this is a good way to get an implementation that is not extremely long. Okay, because almost every check, I mean all the transversing of the graph is done in two functions. One that checks paths and one that checks for connectivity, which is extremely easy. Okay? Also, even connectivity we can use, we can just single out any node because they are all the same if it's a cycle. So we can check one node and then check whether its neighbor have a path between them of appropriate length. So we can do basically all the graph transversals of the entire program is just one function that checks given two nodes is there a path between them, or given one node is there a path starting here of given node. Okay. And since we know that, and this we don't even need graph transversal because we know that the nodes in the middle are going to have degree 2. If they don't, then something's wrong, so we stop. Okay, so we can just greedily iterate through the nodes. Okay, we don't even need DFS or BFS or any kind of graph transversal. Okay, any question or some other good idea to cut short the implementation of this long code? Other good ideas may be to iterate through, like fix an edge or fix a node and then try every possible node to see if is this node exactly that node. But here we have the degrees that make it easy to single out nodes. Okay? But the number of nodes was not so big, so we can also iterate and check. Okay, any comments, questions? Okay, I want to have some time for the difficult problems, so I'm going to speed up. So we already have almost the first 4. So I think the other problem more teams solved was bowling ball. Did anyone finish bowling ball? No. So let me do the left circuit first. So let's see. This problem had a complicated statement, but if you read some books, this is not a complicated solution. If you didn't read the book, then it's a little bit worse. So the problem is we have some junctions and some wires between junctions, and then there are some pairs of junctions that have a LED connected to them, which is an oriented edge, let's call it. That basically means that. And then to each junction we have to assign some power such that the difference between junctions that are connected by LED is between two values. We have a minimum value and maximum. Okay? And all junctions that are connected by wires have to be of exactly the same power. So basically we start by finding the connected components of junctions, right? Because we know we have to assign the same value to all of them. Okay? That's like the simple part of the problem. Okay, then we can forget about the wires. Kind of annoying having to implement it, but it's not really a big issue. Okay? So then we end up with some connected components of junctions. After doing this first step. And then between some of them, we have an oriented edge. Right? This means that there's a LED with one of the pins here and one of the pins here. Okay? We may have self edges also. I mean, in the input, so we have to check for them. Okay? So if there's a cycle in this graph, then it's impossible, right? It really doesn't matter. I'm going to, what the idea I have, it doesn't really need to check this. So then let's assign a variable. So let's consider, let's put names, so let's number these connected components. And then let's say x1 is xi is the amount of electricity we give to component I. Okay, so we have some real valued variables or integer valued variables, doesn't matter. Okay, so and then each edge induces two inequations, which is basically which are all of the form xi minus xj is less or equal than the maximum difference allowed for a LED and greater or equal than the minimum difference. And then what we are asked is whether, so can we assign values to all the variables such that all these equations hold? And if so, which is the we need to minimize the maximum of all the variables. Okay, this is the problem. So first, or maybe we do it in each check. So we first check for cycles in the graph, right? If there's a cycle, okay, since each edge, because of this inequality, each edge means that that xi has to be greater than xj, okay, because this is possible. Okay, so then that means if there's a cycle, then we have a set of variables that have to be less than each other, strictly less because this is some positive integer. Okay, so if you have a cycle, then we cannot have a solution. So we check for that. So basically, this is either not going to happen or we are going to find a cycle. But it's important to consider that it can be, the input can be like this. Okay, so if we simply do not consider them, we get wrong. Okay, so then we basically either have a cycle and say, okay, this is impossible, or we get an acyclic graph. Okay, if we find the acyclic graph, we continue. When we continue, we notice that for each connected component, so each connected component we can process separately. We don't really need to, but we can do that. Okay? And in each connected component we have a number of minimal components. A component is minimal if it has no edge going into it. Okay, so it's like it's the initial of any path. Okay? Since the graph is cyclic, this has to be at least one in each component. There can be more than one. And then we can notice that suppose that to the initial, in this case this will be initial, right? So let's move this to the acyclic. And suppose we assign to this a value different from 0. Okay? Then we can subtract. So let's suppose all the junctions have a value different than 0. Okay? Then we can subtract the minimum from all of them. And of course, all the differences are going to be the same, because if we subtract to every value the same, the difference is maintained. Okay? So we know that there's a solution, and of course the maximum always is reduced, so there's a solution where at least one of the values is 0. Moreover, since we know that this edge represents some inequality, the initial junctions have to be 0, or at least are 0 in some optimal solutions. Okay? So we basically assign 0 to those variables. Okay? Initially. So then, this equation right here, we can write as two equations. One equation is this part, and the other we can write as xj minus xy less than or equal to . Okay? So we have a system of all upper bounds of differences. Okay? This is negative, but who cares? Okay? And now we can see that satisfying, so by theorem, I think it's, let me check the number, but I think it's 2.4. So you can, no, sorry, 24.9. So by theorem, 24.9 of Introduction to Algorithms. I'm going to send the number by email, don't worry. Okay, which is a really good book that you should read cover to cover, even the parts that you think you already know. And this theorem says that this has solution if and only if there's no negative. So if we consider these edges on a graph, notice that the graph is not exactly this one. It's similar, but not exactly this. So basically, we put an edge. If you have an equation like this, we put an edge from I to j with weight max diff, and in here we put an edge from j to I with weight minus min diff. Okay? If that has a negative cycle, so a cycle with negative weight, then there's no solution. Why? Well, because if we have a cycle and we add all the equations, we get 0 on the right side, right? Because a cycle is an edge from j to I, an edge from j to I, then an edge from I to k, so xi appears here and xk appears here. Then the next cycle is xk minus something, and we end with something minus xj. Okay, so if we add all the equations of the edges that represent cycle, we obtain 0 less than or equal to something. Okay? So if there's a negative cycle, we obtain an equation that is 0 less than or equal to something negative. So that's impossible. I mean, that's not possible to fulfill. Okay? So if there, and then the theorem says that if there's there's a solution if and only if there's no not negative cycle, and the optimal solution is at the minimum distance in this graph from the source that are the zeros we already greedily put. Okay? So basically we run a minimum path algorithm that can consider negative weight, so Bellman-Ford algorithm, for instance, starting with 0 in the initial node.
Can you repeat this more slowly?
Sorry?
Can you repeat more slowly, please?
Yes, sorry. Okay. So then we have this system of equations, of inequalities. Okay? Now, then, if we build a graph for each, so each of them is basically is basically of the weight xi minus xj minus equal to something. Okay? So for each of these we build a graph that puts between an edge from I to j of weight w. Okay? Note that w may be negative. Okay, so we build this graph. If this graph contains a negative cycle, okay, then we consider the inequalities that represent all the edges, and we add them. We add the left side and the right side. Okay? In the left side, so suppose we have a cycle. The left side of this edge is xi minus xj. The left side of this is xj minus this. The left side of this is this minus this. So basically, if we add everything, the left side gets to 0. Okay? Because, I mean, this gets a negative xj, and here we have a positive xj. Then this one is added in here and subtracted, subtracted in here and added in here. This one is subtracted in here and added in here. So everything cancels out. Okay? So we get 0 less than, and if the cycle is negative, and here, of course, the right side is the sum of the weights of all the cycle. So if the cycle is negative, basically we get 0 less than or equal to something negative, which is impossible. So if there's a negative cycle on this graph, there's no solution. Okay? And if there is not a negative cycle, then a possible solution is the minimum to assign, so select one node as the source node and assign to all the other nodes, which we are going to select the minimal one, and assign to all the other nodes the minimum path from there, from that node to all the others. Okay? And that gives a feasible solution, which is also, since we are using minimum path, it's easy to prove that this is optimal in the sense of the problem. So then this gives a solution, and then for the given solution, we check every variable and return the maximum of them. Okay? I don't really have time to go a lot into more details of this minimum path part, but we can read the book, read the theorem, it's like one page. I'm going to send you an email. If you don't have the book, there's a PDF, I think, on the internet of it. Okay, any other question? If someone wants like a more detailed discussion, we can discuss after I finish this presentation, like during lunch or after the contest. Yeah. But I want to have time to explain every problem. Okay. So we are missing 4, right? So is it okay if I explain one more and then we take a small break? Are your heads lighting up for one more? Okay. So let's do bowling ball. I think it's the shortest one. Very nice. Okay. In bowling ball, we have something like this. And we are given some physics equations that I don't care about because it's just doing some math. But the important part is that we are given the equation that transform kinetic energy into potential energy, and we know the addition is constant in general. So now we are told that the ball is moving through here, and we are asked, and then each time it goes into a valley, it loses some energy. So basically at some point we're going to lose all its energy. or at least it's going to have all its energy turned into potential energy. So we are asked whether the ball finishes in a valley or it possibly finished in a, it's called summit in the statement. Here, because if here all the energy is exactly potential, when it's here, then it's not going to fall apart. Okay, but that's just a border case that really won't affect the solution. Okay? So we have some costs. So first let me simplify a little bit. So, and we are told that the walls on both sides are high enough such that the bowling ball will never go over them. Right? So there's a really high peak here that the ball, basically when the ball goes here, it's going to go up until all the kinetic energy turns into potential energy and then go back down. Okay? Since the energy is only modified, since the total energy is only modified when we get into these valleys, that means that the ball, after the ball loses its energy for getting in here, it's going to go up and down and going to get down with exactly the same energy. Okay? But basically it's going to turn all the kinetic energy into potential and all the potential into kinetic when going back. Okay? But of course when it goes back it's going to lose this amount of energy again because it's going to hit the valley again. Okay? So what we can do, instead of thinking that the ball bounces, which is more uncomfortable for the argument they're going to make, we can think of that this is, we can multiply this by 2, okay? And then put a mirror copy of this in here. Okay? So instead of doing this and bouncing back and start going to the left, it continues, but it loses here twice the energy because it's going to bounce twice in this valley. Okay? Possibly it's not going to bounce one, but if it doesn't go up and back again, it's because it's going to stay here, so it doesn't really matter if we make it lose more energy. Right? Okay? You see why this is the same? Because I want just all the movements to be from left to right because it's simpler to. Okay. So then we put some other copy, and then we can consider this slightly different, but actually the same problem. And then, so here we have again C5. Well, this is stupid because this is not a mirror copy, but so we have here C5, C4, E3, E2, C1, and C1. Okay. So what we are going to do is, now we think that the ball basically after hitting this valley is magically transported to the other end and keeps doing this. Okay, so it always goes left to right, and when it gets to this end, it's transported magically to the other end, right? So it's basically because this is like a round. Okay? Now, for each peak, we know we have a lower bound on how many energy we need to be able to go over it. Okay? So suppose we are here after we subtracted the energy loss because of hitting this valley. There is some amount of energy that the ball needs to be able to go all the way up and back down instead of stopping in the middle and bouncing. Okay? I don't know how much, but there's some amount. So, and this amount is actually the potential energy of being here minus the potential energy of being here. Because all we need, so strictly more on that, so all we need is that the kinetic energy that the ball has, some of it is going to be turning into potential when going up, right? We need that we have a little bit more of kinetic energy that the amount of potential energy we are going to be producing, so that some kinetic energy remains when we are at the top. Okay? As long as positive, the velocity really doesn't matter. As long as some number of kinetic energy exists, the ball is going to keep moving. Okay? Okay, so then by noticing the difference in height between this and this, we know how much energy the ball needs to pass from this side to this side. Okay? As long as it comes with that amount of energy or more, it's going to pass through. And we can calculate the number from. Notice that the reason that I mirror is that the amount we need to pass from this side to this side is different than the amount we need to pass from this side to this side, because the height difference is different, or possibly different. That's why I'm mirroring. Now each peak has a single cost, because we are only passing from left to right. So basically the cost of passing from right to left here is basically reproduced in the cost of passing from left to right here. Okay? So now we have this kind of bulbs that only allow the ball to pass if it has sufficient energy. And also, each time we pass, since we end up in a valley, we lose some energy. Okay, so we have a minimum and we have some loss, but they are not necessarily the same. Okay, the minimum may be greater or less than the loss. Okay, so we have a minimum that we need to pass, and we also have some payment to do each time we cross. Okay, so then, so we start by calculating. Okay, suppose we are going to pass all the peaks, all the summits. Okay, how much energy is going to lose in an entire round? Well, it's going to lose basically the summation of all the costs of all the valleys, right? Just to make a complete round and come back. So then we know it can go from here to here, just losing this amount, as long as the total energy doesn't go below some number, which is basically the more expensive peak to pass, right? So we have the current energy, and we have the maximum peak, the maximum cost peak. So basically we know that we can just keep doing rounds losing energy as long as we lose less than this in total. Okay? So we can basically simulate by doing nothing this number divided by C1, C2. Well, everything twice because it's going to be the summation of all of them. Okay, so we can simulate, so not simulate, actually just subtract this from the energy, because it's this number of rounds. So we're going to have this number of rounds. With the first this number of rounds, nothing is going to happen other than the ball going from here to here and going back and losing some energy. Always the same for this number of rounds. So we simulate this number of rounds just by subtracting these times the cost of round. Okay? So these first number of rounds are going to be all the same, and all of them are going to lose this amount. So first, so if the ball doesn't start at the beginning, first we simulate by hand the first round until the ball reaches the left end. Okay? But that's just one part. Simulating is just each time we are in a valley, we check, do we have enough of energy? Yes, we can. Yes, we do. Then we put here and we subtract this. Do we have enough energy to pass the next peak? Yes, we do. When assuming we have energy to pass all of them, when we get to the start, we do this of simulating everything. Okay. So, after we do this, we know that in the next pass, there is one peak that we are not going to be able to go over. Either we're going to stay on top or we're going to bounce back. Okay? So we can do the simulation by hand and see what happens. Right? We know we're not going to reach the end. If the ball stays on top of in a summit, in a peak, then okay, we have an answer. If it bounces back, then up from now it's always going to bounce back in the same mountain. Okay? So we can basically remove all the part of the product that is after that part. Right? Because it's never going to gain enough energy to pass once it doesn't have enough. So suppose we find that this peak cannot be passed in this simulation, so we basically remove from here to here, we remove. Okay? Now basically we have a smaller problem. Okay? So eventually we are going to find either that the ball stays in a peak, and then we have a solution, or we are going to reduce the problem until the problem is like this, and the ball cannot reach any top, so we know where it's going to end up in this value after some number of rounds that we don't care about how many. Okay? Now notice that, so see, each time we are reducing, the number of reductions that are needed is linear, maybe less, but at least each time we remove at least one peak. Okay? So the number of reductions is linear, and for each reduction we need linear time to do some simulations. Okay, so in total is quadratic time, which fits perfectly in the timing. Okay? Notice that after removing we have to do this analysis of, okay, now simulate fast again the first round, doing this kind of analysis, then one simulation by hand to know exactly where it's going to stop, or whether it gets on top of a hill or not. Okay? There's a way, I'm not going to explain, but there's a way to speed up this to n log n by doing some sorting tricks with the costs, and then doing basically everything I said symbolically. Like you have the accumulated function of this, and then the removing and everything can be done symbolically to speed up the question, but it's already pretty mathy with just this implementation, so, and we don't have really enough time, so I'm not going to explain the full details of the optimization. Okay, so now we're not really having a really lot of time, so let's take a really small break. Like, let's be here. I'm going to start talking again at 25 to 11, so in 5 or 6 minutes. Okay, so hopefully to last, but something, bring something.
Você consegue chegar aquela condição de dúvidas?
Does anyone in the back wants to step outside and call maybe if there's someone in the hall? Start with you. Thank you. Teaching hazard, since at least some students were trying it. Okay, so the first thing that we need to do for this problem is knowing how to calculate the number of trailing zeros in a given. So the problem asks, so for a given base, we can calculate the number of trailing zeros in a factorial, in a big factorial, and ask for a particular factorial the number of pairs of bases such that when the factorial is written in those two bases, the number of trailing zeros is the same. And as long as this number of trailing zeros is more than some lower bound. that we get. Okay, that is not really too important. Okay, so the first thing that we need to do for this problem is to know how to calculate efficiently the number of trailing zeros of a factorial in a given base. Okay, and the statement already gives us a hint on how to do it, saying how many times a given prime appears as a factor in a factorial, right? Which is also not so difficult to calculate. So we know that p to the k divides n factorial for every k less than n over p plus n over p squared plus so on and so forth. Well, in the same it says up to infinity, but actually up to log in base p of n. After log in base p of n, all of these are going to be 0. So this summation actually only goes finally to p to the log base p of n. Okay? Good. Then this is the multiplicity of a given prime. Prime p. It's very important. Prime. Okay. So now suppose we have a base that is a composite number, right? It can be p1 to the alpha 1 times p2 to the alpha 2 times something like this. P, no, not K. Pm to the alpha. Okay, then. So how many trailing zeros? So this is base B. How many trailing zeros will the n factorial have in base B? So basically, the number of trailing zeros is basically the highest power of B that divides n factorial. That divides, n factorial. Okay? So it's going to have at least one trailing zero if n factorial is a multiple of B. It's going to have at least two trailing zeros if n factorial is a multiple of B squared, and so on and so forth. Okay? So we are actually looking at the highest power of B that divides n factorial. So basically, and the highest power, so basically when we take B to the K, it's basically P1 to the alpha 1 times K times P2 to the alpha 1 to the alpha 2 times K, and so on and so forth, and to Pm to the alpha m times K. So basically we need each of these factors to divide n factorial. Okay? Because we know how to calculate for prime, so it's good that we can separate, right? The number of factors of a given prime in a factorial is totally independent of the number of factors of any other prime, in some sense. Okay? So, and then, so basically we can calculate for n factorial how many factors of the way P1 does it have, and then divide by alpha 1, and then we obtain a possible value of K. Right? And so if we want this to divide n factorial, we want n factorial to have at least alpha 1 times K factors of P1, at least alpha 2 times K factors of P2, at least alpha m times K factors of Pn. Okay, so we can calculate the number of factors it has for each Pi, and then divide those numbers by alpha I. Okay, and the maximum of this is the maximum possible value of K. Right? So it's the maximum K such that B to the K divides n factorial. Okay, so this is a more or less efficient way to calculate it. Okay, remember that n can be really big. Note that this, even if n is big, this summation does not really need a lot of terms, right? A logarithmic number in B. So calculating this by just brute force, let's say, it's logarithmic in n, so it's not really an expensive operation. Okay, so what we do at the beginning, we pre-process, first at the beginning of the program, let's assume we pre-process all the primes that make sense, so primes up to the maximum n. Okay? Because as you can see from here, if p is larger than n, then this is 0. Okay, so we only care about primes up to the maximum n, which is, I think, is 30 million. 3 million. No, 10. No, sorry, 100,000. Okay. So we calculate all the primes that we can possibly use, so primes up to about 100,000 at the beginning. And then for each test case, we pre-process for each prime, we calculate how many times it appears as a factor of n, for each prime less than n. Okay? So we have n, and we have some collection of primes, so 2, 3, 5, blah, blah. And for each of these, let's say we have C sub 2, C sub 3, C sub 5, which is the number of p factors. So this means that 2 to the C2 divides n factorial, and 2 to the C2 plus 1 does not divide n factorial. Okay, so C2 is the largest, is the exact number of factors of 2 that there are in n factorial, and the same for C3, C5, and all the other primes. Okay, so we pre-calculate this. For this, we only need for each prime, which there may be a linear, it's not linear, but it's at most n, let's say, primes. And for each of them, we do some logarithmic process, so it's less, pre-processing all of this is less than n log n. Okay? It's actually linear, but doesn't matter. Let's say n log n. Okay? It's easy enough. Okay, so now that we have this pre-processing, we can think, okay, so now we know that the number of trailing zeros, right, cannot be more than some of these, right? Because we already said that to calculate the number of trailing zeros in a given base, we're going to have to figure out the number of factors of a given prime, then divide by something, And then we are taking some maximum over this. So the number of factors of the primes in n factorial of the primes that divide the base is an upper bound on the number of trailing zeros of the base. Okay? In particular, the maximum of this, which is C2 of course, because this equation is clearly decreasing with P. So C2 is an upper bound on the number of trailing zeros in n factorial in any base. Okay? Is this clear? Good. Now, how big can C2 be? Well, from this we can see that C2 is logarithmic in n. In n factorial, sorry. And logarithmic in n factorial is basically linear in n. Right? We can also get it from here. This is basically, so the number of factors 2 is n over 2 times plus n over 4 plus n over 8 plus n over 16, and you know that this is less than 2 times n over 2. Okay, because each of these is bigger than all the summation of all the rest, even up to infinity. Well, up to infinity is equal. Okay? So we know that C2 in less than or equal to n. Okay? Because it's 2 n over 2. Okay? Good. And of course all the others is something. Okay, so now we know that there's at most n, at most C2, which is at most n number of possible values for trailing zeros. Okay, so we iterate trailing zeros from x, which is the minimum value given by the statement, that can be 2, but it doesn't matter, to C2, which is the maximum possible number of, so we fix the number of trailing zeros. And for each number we are going to calculate with some combinatorics how many pairs of bases have exactly, how many bases have exactly this this amount of trailing zeros, and then add the square. Or not the square, the n times n minus 1 over 2. Right, the possible pairs among all these set of bases. Okay? So all we need to do is calculate pretty efficiently, because this is a really large amount to process, how many bases have a fixed number of trailing zeros for n factorial. So for how many bases n factorial has a fixed number of trailing zeros. Okay? Is this okay? Good. Okay. So let's suppose we want the base to have, so suppose we want some b to have some fixed number. So let's call this is trailing zeros, let's call it t. Trailing zeros. So we have some fixed value t, and we want one base to have exactly t trailing zeros for n factorial. To have exactly t, it needs to have, the base is going to have some prime factors, all of which are going to be among the set of primes we are considering. And for at least one of them is going to have the power of the factor be, so we have all this amount, right? So let's say, let's call this P1, P2. Oh. So let's say P divides B, some base. Okay? And we have some prime factor. P is a prime that divides B. Okay? And so since you want t trailing zeros, we know that. So let's say P to the k divides B, and P to the k plus 1 does not divide B. Okay? So basically P is a factor of B with multiplicity k. Okay? So now we want, we're going to do this alpha. So let's say. Okay, so now we want alpha. So we want t over alpha to be, sorry, we want Cp over alpha. We need it to be less than or equal to k, right? Sorry, greater than or equal to k. We need to be, with n factorial, we need to be able to build at least t times alpha factors, t times alpha factors of p, because we want b to the we want b to the t to divide, n factorial. Okay, so we need a prime factor of multiplicity alpha in b. We need p to have alpha times t factors in n factorial. So Cp factors. Okay? So Cp over alpha has to be less than, greater than or equal to k. And also we want for at least one prime, for at least one of the factors, we want this to hold, for the equality to hold. Right? To be exactly t. Okay? So for every prime, this has to happen, and for some prime, this equality has to hold. After round. Okay, so this equality. So the equality that has to hold is Cp over alpha is equal to 1. Okay, because we can have some left over. Is this okay? Okay, so then we are going to do some dynamic programming here. So for a given t, this has to happen, right? So then we are going to consider only the CPs. So we need, in particular, since alpha is at least 1, we're going to use the CPs. I mean, when alpha is 0, we're going to just skip the prime. Okay? We're not going to consider the prime. The prime is not the factor. So alpha is at least 1. So we're going to consider CP is also greater or equal than t. Right? Because it's greater or equal than Cp over alpha. Okay? So then we only need to consider the primes such that Cp is greater or equal than t. Okay, so then we can find here with binary search on this array, we can find the subset of primes. Efficiently, we can find the subset of primes such that Cp is greater or equal than p. We sort this in reverse, actually. So C2 is going to be at the end. Okay, this is a decreasing array. Okay, because this function right here is decreasing when p increases. Okay, so with binary search, we can find a prefix of this array such that all the p's, all the possible p's that are smaller, such as Cp is smaller than t. Moreover, this decreases extremely fast. Okay? So this number, so the number of p's, such that Cp is less than or equal to t, the amortized cost of the summation of these numbers for every t is going to be C2 log C2, so n log n. Because this is basically the same analysis you do for Eratosthenes sieve, and the same we did yesterday. Okay? Because remember that, so we said that C2 was less than or equal to n. So basically C2 is less than or equal to n because it's actually C2 is less than or equal to 2 times n over 2. And then C3 is less than or equal to 2 times n over 3. And C5 is less than or equal to 2 times n over 5. Okay? So basically Ck is more or less linear on n over k. Okay? So that's why this number, as t gets bigger, this number gets smaller and smaller to be extremely small in the end. Okay? And the total amount is going to be n log n. Because it's basically t over is 2. So this is bounded by t over the maximum p. Okay? So, sorry, this is bounded by n over t. Okay? Good. So this is an iteration we can do, but we're not going to do really an iteration, we are going to do some dynamic programming function calculate that takes this amount of time. So the function is, okay, among this set of primes, how many combinations we can make such that this condition is fulfilled. So for every prime, to each prime we assign some alpha such that this is true, and to at least one we assign alpha such that this is true. Okay? But then this is more or less easy. I mean, this is a regular dynamic programming technique, right? So we iterate the primes. So our recursive functions have some index that iterates the primes. We have fixed t. And then we calculate for each prime And also we maintain a Boolean variable to see whether if we already chose a prime such as this is fulfilled or not. Right? So when we get to the end, if we didn't, then we return 0. If we did for at least one prime, then we return 1. Okay? And then the possibilities are, so we process prime P. P is for the prime number P. That number I, sorry. And then we want to count for how many alphas this is true, and if for at least one alpha this is true, but this is just, we can do this with simple math, right? Because the number of alphas, number of possible values for alpha such that this is true, we can calculate as Cp over T, right? And rounding. Okay? And then we are going to check whether there is one value of alpha such as this is true, and we call recursively, putting the Boolean variable in 1, and then we calculate for all the other values of alpha. We know how many there are, so we call recursively and we multiply by the number of possible values. Okay? Okay? This is clear? Good. So then with this dynamic programming function, we calculate the number of bases for this given T. Then from that number, we can know the number of pairs for that given T, and then add up all the possible pairs. Okay? And as I said, this is clearly linear on the number of primes we consider, because this is linear, this is 2, this is the number of primes, this is 2, and then the process we need to do inside the recursive function is constant time, because it's just some calculations. Okay? And I already argued that this total number of primes adds up to n log n amortized time. Okay? So then this part is also n log n. Okay? Okay. So now, any questions, any other ideas, comments? No? Go. The next, let's do mixed finite plans, which is the last one in the topic. Sorry? Okay. So in this problem, we are given the information about some flights. We have some direct flights and some complicated flights, which are basically sequences of airports. And we are told that we need to send one guy from A to B and one other guy from C to B. From C to D, sorry. But we can either do that, or we can send one guy from A to, we can exchange the destination airport as long as we choose a flight plan that intersects in some intermediate airport. Okay? This is the statement in a nutshell. So of course we build a graph in which each airport is a node. One important thing to notice is that these indirect flights that you can buy that have several sequence of airports, they are all different, so the maximum number is the number of airports. Okay, because there was no bound in the input section even for the number of airports of the plan, but in the statement it says that they are all different. So at least we know that there are less than the number of airports. And the number of airports is not too big, it's like so we have n airports less than 100, or n nodes at most 100, and we have some edges. And the number of edges was 10,000 edges. So let's put all the direct flights are edges, and for each non-direct flight we can also add an edge for each way to use it, right? The statement says to use a sequence and a direct flight, so a sequence of airports, we can use it from the first to the second, from the first to the third, from the first to the fourth. So we have to always start at the beginning, but we can get off at any of the intermediate airports. Okay? So we can build a graph of all the possible trips. Okay? And the graph is going to have the original, so it's going to have less than 10,000 edges from the number of flights, plus we are told that we have at most 1,000 of those are indirect, and the 1,000 induce at most 100 edges each. Okay, so the total number of edges is going to be less than this, which is more or less manageable. As long as we do linear things on M, it's going to be fine. Okay, but M can be big. Okay, so now we're going to consider several options. So the first option is just make the first guy go from A to B and make the second guy go from C to D. That's easy to calculate, right? So if we run this algorithm starting at A and starting at B, we calculate the distance from A, so actually the cost of going from A to J for every J, the cost of going from from C to J for every J. So basically, if we want to send them direct, we can calculate that the cost is this cost of A, B plus cost of C. So that's one option. Okay, one cost option. And this Dijkstra algorithm we can calculate in M log n. Okay. Okay. So the other option is to make them meet and to make the A guy go to D and the C guy go to B and make them meet at some intermediate A point. Okay. So let's first consider the simpler problem of there are no indirect flights. Okay, so we don't have this option of buying something and getting in the middle because so no indirect flights. So in that case, if we do a Dijkstra on the reversed graph, we can calculate the cost of going from any I to P and the cost of going from any I to D, also with Dijkstra algorithm, but just by reversing the edges. Okay? And then try every possible, and then for each intermediate J, for each intermediate airport, we sum the cost of going from A to J plus the cost of going from J to D plus the cost of going from B to J plus the cost of going from J to C. Okay? If we fix that they meet at airport J and we try that for every J. Right? But for every J we only have to do an addition once we have all these costs pre-calculated. Okay? Now the problem, so this is there's a problem in Sposh that we use in an Argentinian competition a while back. It's called Charlie and Nito. If you want to try it, that is basically this idea. So if you didn't know this idea, you can practice this much simpler problem that is just using this idea on okay, let's recalculate how to get from the start to the meeting point and from the meeting point to the end, and then try every possible meeting point. Okay? Notice that this is much better than trying the meeting point and then calculating Dijkstra depending on the meeting point. We don't need actually the minimum path from everywhere to everyone. Right? Because every minimum path that we need either starts at the starting point or ends at an ending point. Okay, so we only need 4 runs of Dijkstra. Okay? Okay. So then the problem is that some of the edges may give us the path through J for free. Okay? I mean, if some flight plan, so if J, so if J is 3 and some indirect flight has 5, 2, 3, 4, 9, and we are going to use and maybe it's a good idea to use this edge from going from 5 to 4, but this already gave us for free that we pass through 3. Okay? We are not required to stop and take a different costly flight after passing through the airport. Okay? We can just continue on our current flight plan for free. Okay? This is what the last thing we have to consider. Okay, so for this we have to do something slightly more difficult, but not so much. Okay, so first we can calculate, so now this is basically the cost of one guy going from A to D passing through J, and the cost of the other guy going from B to C passing through J. Okay, so we can calculate all those two costs independently. Right? I mean, once we fix where they are going to meet, they don't care what each other does. Okay? So So then basically we are going to have a function, I'm going to show you how to calculate for this guy, and the other guy we do the same, but using, so for one guy we use these two pre-calculated tables, and for the other one we use these two pre-calculated tables. Okay? So we want to send one guy from A to D passing through J. Okay, so then what he's going to do is go from A to some I, then, okay. So then first we consider this possibility so the possibility of the guy actually going to J, dropping in J, and then taking a different flight. Okay, so one possibility is cost from A to J plus cost from J to D. That's one way of doing it. The other way of doing is using an edge that passes through J in the middle, right? But we're not actually using it to go to J or to leave J. We are using it to go from I to K, and it happens to pass through J. Okay? So basically, we are going to calculate the cost of going from A to I, and then the cost of going from K to D, and then plus the cost of an edge that goes from I to K and happens to pass through J. Okay? So for this to work, so we can try every possible I and K, right? Because this is going to be cubic in total. We have to do it independently for the two guys, right? But here we can try, here we're trying every J, we can try every I and every K. Okay? As long as we can do, as long as we know how much this costs in constant time. Okay? So this we already know. We have pre-calculated in this table. Okay? This also we know. So what we have to know is for each triplet ijk, how much does it, if it's possible, otherwise we put infinity, how much does it cost to go from I to K passing through J? Okay? And this we can calculate just by examining the indirect flights. Right? If we have some indirect flight that says 3, 5, 6, 8, 9, since we know I has to be this value, okay, we try all possible in a pre-processing stage, we try every possible pair of this other that ordered such that they can take value of J and K. So we try J equal 5, K equal 6, J equal 5, K equal 8, J equal 5, K equal 9, J equal 6, and so on and so forth. All possible pairs. Okay? That takes n squared time for each of the indirect flights, but the number of indirect flights is small. Okay? It's 1000 times n squared, which is 100, that's fine. Okay? So we build this table of, for each ijk, we remember, and then that when we have a triplet here, ijk, we know that there's a possibility of some cost that we have here, cost that we know. Okay, so it's possible of going from I to K passing through J at this cost, using this indirect flight. Okay? So we check this for every indirect flight, and then we build the table for every triplet. We maintain the minimum cost of going from I to K passing through J, because there can be several possibilities.
It's impossible to take an indirect flight from the middle.
Yes, it's impossible. Yeah. The statement says that you have to take it at the beginning. That's important. When we reverse the edges, we have to consider, so for the regular vector, we consider all these edges, right? For the indirect flight. For the reverse, we don't consider. So we have to consider the reverse of this. Okay, so starting at any of the possible finishes and always finishing at the beginning. So we reverse the actual edges, not reverse the entire indirect flight. Okay, it says in the statement that the indirect flight has to be taken on the initial airport, which is actually a true policy of at least most airlines. That you cannot take, if you buy the continuous plan, you cannot take it in the middle. If you miss a connection, you miss all the others. Okay. So that's why we can calculate that in time n squared times the number of indirect flights, which is some smaller m. We can calculate the number of, for each triplet we can calculate the minimum cost if it's possible to go from I to K passing through J, and then with this table we can have this pre-calculated in constant time. Okay? So we try every possibility, and then we find the the least expensive way from going from this guy to go from A to D, passing through J. Then we process the same, but from the other guy from B to C, and we add up those two minimums, and that's the minimum way for the guys to deliver the packages passing through J. Then we take the minimum of above every J, and we compare that with the minimum of not exchanging the packages, so going directly, that we already knew how to calculate. Okay, and that's the answer to the problem. And of course, we put some infinities, and if the minimum is infinity, then it's can be done. Okay? Any questions about this? Good. Any other idea, other approach? So the last problem is wedding hall. Also my favorite problem. Okay, so the statement is simple to explain. We want to build some L-shaped hall, and we have some area in which we can build it, and in this area there are some trees, and we cannot build the hall with the tree inside, and we cannot cut the trees down or anything. And we want to know, okay, what's the largest thing of this shape that fits in here? Okay? So the first step is the easy idea. Let's do binary search of the size. Of course, if some size fits, also any smaller size fits. So we can binary search for the maximum size. Okay? One, binary search. So what remains, which is the important part, is, okay, for a fixed size, does it some hole of this size fit in here? This is the question we need to be able to answer. Okay? And since there can be many trees, like 50,000 trees, we have to do it rather efficiently. Okay? So there is more than one. So there's a way, the difficult way to solve this directly, that a friend of mine implemented. But so I think the best way to think about these problems of whether something fits in somewhere, because fitting things is complicated. It's a complicated thing to think about. So there's a duality between this problem and the problem of, can I cover this whole thing with pieces of this shape? And this is why. So suppose we consider a single tree. Okay? So finding a place, so now we have a fixed L shape, right? With a fixed size. Okay? Fixed size. So finding a place for this L shape is finding basically, I don't know, a point for its upper left corner, let's say. We may choose any point. The usual is the upper left, so we want to find a point for the upper left corner. And then the condition is that from there is no tree in some area of the shape of the L. Okay? So we can think of each tree as forbidding some subset of points for being a feasible upper left corner. Okay? Some choices of points as upper left corners are going to make, well, this one not, are going to make the L overlap with this tree. Right? So we cannot choose those points. And it happens that the shape of the area of points, so it's pretty, since this is a kind of a continuous condition, it's pretty easy to imagine that the set of points that are forbidden by a given tree form a continuous area. Okay? So, because it's just like moving. So what's the area? It's basically, we fix a tree. So suppose we put so suppose this is a nail and we put some wooden shaped L like this. So it's all the points I can reach by moving the L like this without getting the nail out. Right? That's why it's continuous. And it will, So, and then we can figure out that the area is actually something shaped like this, but it's going to like flip. So for the region 3, the forbidden area is something like this, shaped like this. Okay? 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 So and every tree forbids something. Of course, a given point may be forbidden because of more than one tree. Okay, if you have a tree here and a tree here, they both forbid this point here. Okay? But that doesn't matter. Okay, so for each point we calculate 3 squares, because it's easy to deal with squares that L-shaped things. And then we want to know if this set of squares covers the whole area. Okay? This is much easier to visualize problem. It's the same problem, but for me at least this is much easier to visualize. So now the problem is given an area, given 3n squares of fixed size, all of the same size, which makes things even easier. Do they cover the whole area or not? Okay, and then that we can solve with the sweep line algorithm. Okay, what's the sweep line algorithm? First, so we sort the squares by x coordinate. Okay, doesn't matter if it's the beginning or the end, because since they are all the same size, the order is the same. Okay, and then we consider all the squares that have x coordinate less than or equal to 0 at the beginning. Okay, so we are going to, so basically squares that touch or overlap with the left side of the area. Oh, sorry. One more thing is that we have to modify the area that is feasible for upper left points in not exactly the same area as given in the input. Right? We cannot choose like this point, because the L is not going to fit. So if we are given, I don't know, W times H, then we need to consider H minus T minus 2T and W minus 2T, where T is the size of these squares that we already fixed. Okay? That's the area in which we can choose an upper left point. Be careful that we do need to consider trees that are outside this area, right? Like a tree can be in the corner and still close to the corner, but still forbid something that is within the shrunk area. Okay? So we consider every tree. But then we have to know if this shrunk area is completely covered or not. So this is the area we consider for the sweep line. Okay? The area of the points that are feasible choices will be the upper left corner of the whole. Okay, so now basically we have an area, we have some squares, and we want to know if all the squares cover the area. So first we start with, so we're going to do a sweep line, and what we maintain at each time is the set of squares that are over the line, that overlap with the line. Okay, so of course the stop is when a square starts, we have to insert. When a square ends, we have to remove. Okay, it's important to insert before removing, because if two squares, since it says that the tree can be on the boundary, we have to remove before inserting. Because if two squares are exactly like this, we don't consider this covering, because we can choose this one or any. Okay, so we need the squares to actually overlap to cover the thing, not be side by side. Okay, but then since we are doing binary search, really this is not really important, right? Because if some size doesn't work because of this boundary condition, the same size minus a really small thing is going to work. Okay, so but yeah, if we want to do it more precisely, then we need to consider this not covering. And the way to do that is just first remove the squares. If I find code, then it's not covered, then I insert the new squares. Because a lot of squares can have the same x coordinate, so it may be removed or inserted and in the same step. Okay, actually this is going to happen because for each tree we have these three squares that are, no, we have this and this is covered properly. So let me take this out. So we need to consider this actually covering because of this, right? Because this tree generates these squares, and this part is not actually uncovered, right? We are separating into squares just for easiness of implementation, but those are not actually separated. Okay, so let's consider it covered because the binary search is going to just find the same size minus a really small epsilon to work. Okay, sorry about that. Okay, so we need a line. So then to initialize, we need to find out which squares are initially inside. So we consider all the squares that have one x coordinate less than 0 and the other one more than 0. Okay, so the ones that have the x coordinate more than t less than x 0, so more less than minus b, those we remove, right? Because they are completely outside. They are completely to the left. We can actually remove everything that doesn't overlap with the area when generating. And let's assume that every square has at least some overlapping with the area. Okay, so first all these initial squares we insert into a set, and this set we sort by y coordinate. Okay? Yes? So then we check for the initial set to have no holes inside. So the set is actually, so h squared, when looked at as a vertical thing, is a set of intervals, all of the same size, so it's easy. When sorted by y, we just need to check that each square overlaps with the next. So we check that for the initial set. Then each time we insert a new square, of course, if everything was good, it will still be good. But then each time we remove a square, we need to check whether we produce a hole, right? In our set of squares. But that's easy because when we remove, since we have it sorted by y in like a set, in a standard library set, we can check the all previous and next squares of the one we remove that we can find in logarithmic time, and then check if those two overlap. Okay, so we have a set like this. Which is sorted by y. So if we, right, this we maintain when the line is like here. So we are going to remove some, so let's call this 1, this is 2, this is 3, 4. This is in which order they are in the set, right? So if we remove number 4, we have to check whether number 3 and number 5 overlap. If we remove number 2, we have to check whether number 1 and number 3 overlap. Okay, because they are in order and they have all the same size. So if there's overlapping, we only need to check consecutive ones. Okay? So when we remove, we check. If they still overlap, then we didn't produce any holes. If they do not overlap, then okay, we found the hole in the covering, so this size works. Okay? This size is small enough to work. Okay? Do you understand? So this part is n log n because basically we have 6n places to stop the line. We have 3n squares and two places where we have to stop per square. Okay, so at most 6n places to stop. Actually, it's going to be a lot less because of this, there are going to be a lot of overlapping between the x coordinates of the squares produced by the same tree. But 6n is still linear in n, and then for each stop, we need. I mean, for each square, we are going to do two operations. Once we are going to insert it, and once we are going to remove it and search inside the set in a sorted set, so searching logarithmic time from its previous and its next, and compare. So all operations that we can do in logarithmic time. We're going to have n log n in total for this process. So we're going to have n log n times some log of the precision for the binary separation. Okay? Any questions? Any different idea? Okay, so I think that, I mean, this sweep line is more or less standard sweep line algorithm. Is interesting to implement if you are not extremely comfortable with sweep line. But I think that the good idea to take from this problem is this duality, right, between covering and finding a place. Right? For me, at least, understanding what happens when trying to find a place for something. Because I guess for the same reasons probably can be solved directly with sweep line, right? But I find covering much easier to visualize and to understand that I find, okay, do I have a room for to place this? Because when we change to covering, we can make these three squares independent. Well, these three squares independent, and that we cannot do when we are trying to find a spot for the whole thing, right? I think that makes a big difference. in the easiness of understanding and then implementing also. Okay, any other question or comment in general? Okay, so some general comments about yesterday's contest and also maybe a little bit about the week in general. So yesterday we had a set of difficult problems. So and several teams had a relatively large number of wrong answers. Okay, and it seems like even problems with 9 wrong answers, 7 wrong answers. Don't worry, I don't remember which teams. I don't really care because this is training. This is when this kind of thing is supposed to happen, right? The whole idea is that this hasn't happened in the actual round. So and the problem about the wrong answers is not the penalty, right? So if you have lots of wrong answers on the last problem you solve, I think that's fine, right? Or in the last half an hour of the contest, if you are debugging 2 problems and you are submitting all the time, I find that the regular thing to do. But if you're coming with a lot of wrong answers in the first, second, third problem, in the first 3 hours or 4 hours of the contest, I mean, wrong answers are not only 20 minutes for a penalty. Wrong answers are a lot of time for you not to be thinking, right? Even if you, because I think that I find that some teams, not necessarily you, but some teams may say, okay, at some point I don't care more about the penalty, I need to win by problems. First of all, this is a fallacy. This is not true because if all teams with the same number of problems think that, then the penalty is important. But even if you don't care about the penalty and you only want to solve some number of problems, doing this, I think this is wrong, so submit and try because I don't care about the penalty, it's not true that that takes a negligible amount of time. Because you're interrupting your teammate that is in the computer, and you're losing focus, and you're also like making the change and submitting, waiting for the answer, and being nervous about whether this change is going to finally solve the bug in your code or not. And all of this really makes you lose focus from thinking on the problem. So if you are submitting every 5 minutes, you never have like 15 minutes straight to think about your code or think about the problem again and really come up with the idea of where the bug may be or where the hole in your idea may be. Okay? So believe me when I say that in the World Finals the problems are going to be much tougher than in the regional, and start working as you work the last 3 hours of the regional from the beginning of the World Final. Right? Don't rush into, don't think that you need to have a problem ready by the first 30 minutes or otherwise you are screwed. Right? This may be true if you want to get a World Final spot, that if in the first hour, in the first hour you solve nothing in the regional, yeah, you're probably too much behind. But in the World Finals it's not true. It's easy to solve, since the aim is not 8 but 6 problems maybe, something like this. I mean 6 problems at least in the last years it will be a really good performance. You don't really need even a single problem solved in the first hour, right? If you solve 2 problems in the first 2 hours and you already have some idea of the others, that's fine, right? And also at the beginning you always start. So remember this, and I try not to rush into solutions and do not waste time just submitting. I mean, if you're going to lose a lot less time thinking for 20 more minutes, being sure of what you're doing, checking with someone that is free whether this fix will actually solve the problem or not, or coming up with a test case that actually tests whether this was solving a bug or not. Because sometimes, okay, you found the bug or you find the -1, but since you're already out, you already have the printed copy, take some extra 5 minutes or 10 minutes and check the whole thing, right? Or check the whole idea again in your head while the printed code comes. Okay? So I think that's something to analyze besides, okay, I got these problems and this problem. So I think, so my idea for this week was, like the whole training was driven by this idea of trying to get you into World Final mode for solving problems. So do not rush into things, try to be more patient, solve longer problems, this kind of thing. Come up with edge cases from the problems which may not usually appear in the Latin American regional, but usually do appear in a World 1 finals problem. Solve some long backtracking or long implementation problems that are not really difficult but just long. Okay, so this is the driving idea of the whole work. So for that to work, okay, you have the practice of being in the contest, but also after the contest or after the week, if you are too tired after the contest, look at the result, remember what happened, how many times you submitted, how much time did you spend waiting for some submission result or something like this, and then try to analyze if you should change strategy, if you should abandon some problem and go back to it later. Because if you have no idea why it's failing, maybe it's good to put it on hold for a while, think about some other thing, and then you go back. Or sometimes maybe even never go back to the problem instead of spending, I don't know, 3 hours on a single problem. Even if you solve it, it may not be economical to do. Okay, so to summarize, to take more advantage of this, analyze what happened in the contest, after the contest, not only with the problems but also strategically. Okay? And I know when you practice and you simulate the contest in the future, try to have some additional constraint of what you're going to do. Okay, so today we're not going to resubmit in less than 10 minutes. Like something like this. If you find yourself doing that all the time, I'm failing. Right? So if you find that that's happening, maybe have some constraint like this, like fixed time, or be especially concentrated on not doing this resubmission without double checking, so that you get used to doing that, and then when you are in the finals, this will come naturally. Okay, the finals is not really the best place to learn. Right? You have all these training exercises to learn. Okay, so that's it. So I think Rodolfo wants to come and say some things.
Thank you for being with us this week again. Thank you. Thank you all for staying this 2 weeks with us. I'd like to invite you to send several emails to me with suggestions, with anything you like and you don't like this week. This is very useful for us. We try to reread